Today, we are going to learn the quantum mechanical treatment of the hydrogen molecule ion. Quantum mechanical treatment of hydrogen molecular ion, H2 plus. Okay, and why we are beginning with this one, because this is one of the simplest systems when we are taking into consideration of the systems of two nuclei. Means we have uh, two hydrogen nuclei here, but we have only one electron common to both nuclei. Okay, so we have the hydrogen nucleus here. Let me call this as a hydrogen nucleus A, and I have another nucleus here. Let me call this as hydrogen nucleus B, and common to both of these nuclei I have only one electron. Okay, there should be actually two electron if it is hydrogen molecule, but one electron is kicked off, that is why it has a plus sign. So only one electron is there. Okay, this is the electron, and this is the system we are going to learn. Why this is simple? Because this system has only one electron. Okay, for electron repulsive potential energy terms will not be present in the Hamiltonian, so that the treatment of this molecular ion will be very simple. Okay, so that is why we are considering this type of a system to begin with, to learn the bonding in terms of quantum mechanics. Okay, and let me explain the system further. And the distance between the nucleus A and the nucleus B, this distance is capital R. Okay, that is the internuclear distance. And the distance from the nucleus A to the electron, this distance. Okay, and this distance is RA, that is small r A, and the distance between the nucleus B and the electron is RB. Okay, so this is how we have constructed the molecule or molecular ion, and we already know about how to treat quantum mechanically the hydrogen atom. We already learned that in the previous semester, so you already know something about these things. Especially you may be knowing what is the oneness wave function. Okay, you may be knowing the oneness wave function. You may be remembering the oneness wave function, and one is 1 by root pi into e raised to minus r, e raised to minus r. This is what you have learned in the previous semester, and at that time we considered that there is a nucleus. This is a hydrogen nucleus, and surrounding the nucleus there is an electron. So it was only a two particle system. Okay, and this has a charge of plus E, and this has a charge of minus E, and this was the system, and the distance between this electron and the nucleus was small r, and if that is the case, the oneness orbital is 1 divided by root pi into e raised to minus r. We already know this. This is an atomic unit. Okay, atomic unit. Okay, now on the basis of this much knowledge, we are going to treat the H2 plus ion or hydrogen molecular ion. And what we are going to adopt here is the method that we already learned in the previous class, that is LCAOMO method, linear combination of atomic orbital molecular orbital method. So here we have to have the wave function psi, which is a linear combination of the atomic orbitals, that is A1 1SA, where 1SA is the atomic orbital of the first hydrogen atom, that is the oneness atomic orbital. There may be many atomic orbitals. We are considering the oneness atomic orbital because the bond is being formed between the oneness orbital and oneness orbital, and here we are taking only the lowest energy atomic orbitals only. Okay, so that our linear combination set is not very big. It contains only the oneness orbitals. So psi is equal to A1 1SA plus A2 1SB. 1SA and 1SB are the 1s orbitals of the A 1s orbitals associated with the nucleus A and nucleus B. Okay, if we are considering nucleus A and nucleus B are the as the individual hydrogen atoms A and B, then 1s A and 1s B are the psi functions. Okay, the lowest energy psi functions or lowest energy solution for the psi, and that is 1s A and 1s B. We are taking the linear combination of those two atomic orbitals. That is what is why psi is called an LCAO-MO, linear combination of atomic orbital. Okay, here 1s A is 1s A is 1 divided by root pi into e raised to minus ra, and 1s B is equal to 1 divided by root pi into e raised to minus rb. Okay, you already know what is ra, and rb. Okay, it is already here. We already mentioned that. Now we have the psi, the molecular orbital wave function, which is expressed as the linear combination of the atomic orbitals. And now we are going to apply the variation method. Okay, we are going to apply the variation method in order to find out the energy associated with this trial function. This is a trial function psi. This trial function is expressed as the linear combination of atomic orbitals. So we are going to find out the energy associated with this one. So the energy associated with this one E is equal to, you already know from the variation theorem, it is integral psi star h cap psi d tau, h cap psi d tau divided by integral psi star d tau. Okay, and here we can substitute. Let us, for simplicity, let us assume that this is a real function. So we can write it like integral psi star is also equal to a1 1s A plus a2 1s B h cap psi, that is a1 1s A plus a2 1s B divided by integral a1 1s A plus a2 1s B, a2 1s B, B is small, okay, a2 1s B the whole square d tau. Okay, and that is and here we introduced the Hamiltonian. Hamiltonian is the Hamiltonian for the system, and we can construct we can define the Hamiltonian also here. The Hamiltonian that we have used in this expression, h cap is equal to, we will express that in atomic units. So it will be minus of del square. We already learned this, how to express this Hamiltonian in atomic units. You can check back the previous video. Okay, minus of del square minus 1 divided by Ra minus 1 divided by Rb plus 1 divided by R. Okay, the first one shows the kinetic energy operator for the electron, the only one electron which is present in the system. The second represents the attractive potential energy between the electron and the nucleus A. The third represents the attractive potential energy between the nucleus B and the electron. And the fourth one represents the repulsive interaction between the nucleus and nucleus, nuclear repulsive interaction. Okay, so this is how the Hamiltonian is constructed. That Hamiltonian only is applied here. Okay, so now we have the task that we have to find out A1 and A2, which are the coefficients of the atomic orbitals here. And you know how to do that in the variation theorem. We have already learned that. In order to get the values of A1 and A2, we have to apply this method, that is dou E divided by dou A1 is equal to dou E divided by dou A2 is equal to 0. Okay, we have already learned this. I hope you remember this. This only means that we are selecting the we are choosing the values of A1 and A2 so that the energy is minimum. Okay. For example, if you are constructing the psi with the different values of A1, for example, okay, and the psi will be like this. Okay, it will be like this. What means here you are taking a1 and here you are taking the energy corresponding to the psi function, then you will be taking the this value where the energy is minimum, and that whatever may be the a1 corresponding to that, that will be the accepted a1. Okay, whatever may be the a1 corresponding to this minimum energy, that will be the accepted a1. And at this portion, okay, where this energy is minimum, you can see that dou E divided by dou A1 is equal to 0. Okay, because it will have some value in both sides of that, because it is, see here, as the a1 is increasing, E is decreasing, so there is a slope, and in the other case when a1 is increasing, E is also increasing, so there is also a slope. Okay, either negative slope or positive slope. But at this point, the midpoint of these two areas, there is a point that is a turning point. At that turning point, the slope is 0. That is why we have dou E divided by dou A1 is equal to 0. And like that, we have to select A2 also. So all the coefficients of the atomic orbitals are selected in such a way that the energy is minimum. Okay, energy corresponding to that is minimum. So that is why dou E divided by dou A1 is equal to dou E divided by dou A2 is equal to 0. And before expanding this equation, we have to expand the function for E. Therefore, E is equal to, I have already given the expression for E here. Okay, this one. Okay, E is equal to psi h cap psi divided by integral psi h cap psi divided by integral psi square d tau. Okay, I am going to expand that. When I am going to expand that, that is a1 square E is equal to a1 square 1 as a integral a1 square integral 1 as a h cap 1 as a d tau. Okay, that is this term and this term together. Okay, this term is operated by h cap, so that is why a1 square 1 as a h cap 1 as a d tau plus a2 square integral 1 as b 1 as b h cap 1 as b d tau 1 as b d tau. This is this term and then this term together. Okay, a2 square integral 1 as b h cap 1 as b d tau plus a1 a2 integral 1 as a 1 as a h cap 1 as a h cap 1 as a d tau plus a1 a2 integral 1 as b 1 as b h cap 1 as a so here it was a1 a2 1 as a h cap 1 as b d tau. Okay, 1 as h cap 1 as b d tau, sorry, 1 as b d tau. Here it is a1 a2 integral 1 as b h cap 1 as a 1 as a d tau. Okay, so these are the terms on the numerator divided by the denominator, integral 1 as a plus a1 1 as a plus a2 1 as b the whole square d tau, that is equal to a1 square integral 1 as a 1 as a d tau 1 as a 1 as a d tau plus a2 square integral 1s b 1s b dito plus 2a1 a2 2a1 a2 integral 1s a 1s b dito. Okay. Okay. Then that is equal to okay, this one, that is equal to a1 square. I write integral 1s a h cap 1s a as HAA. You may be remembering this type of notations. We learned this while learning variation theorem. So let me write this as HAA. HAA means integral 1s a h cap 1s a dito. Okay, plus a2 square integral 1s b h cap 1s b dito. I can write it as HBB plus then we have to write a1 a2 integral 1s a h cap 1s b dito plus a1 a2 integral 1s b h cap 1s a dito. Okay, this is HAB and this is HBA, HAB and HBA. Okay, and HAB and HBA are equal because the H cap is a Hermitian operator, so we can write it like 2A1 A2 HAB. Okay, divided by a1 square integral 1s a 1s a dito. I can write it like SAA, okay, plus a2 square integral 1s b 1s b dito is SBB plus 2a1 a2 integral 1s a 1s b dito, that is written as SAB. Okay. Now we are going to use our equation that I just mentioned above, that is dou E divided by dou A1 is equal to dou E divided by dou A2 is equal to 0. We are going to choose the values of A1 and A2 by expanding this equation. Okay, so let us find dou E divided by dou A1. Dou E divided by dou A1. Dou E divided by dou A1. And it will be very difficult if we are finding out dou E divided by dou A1 right from here, because E is A1 square HAA plus A2 square HBB, like that. Okay, many functions are there. Since many functions are there, we will shorten this. We will call the numerator together as n and the denominator together as d, where n is equal to a1 square HAA plus a2 square HBB plus 2a1 a1 a2 HAB, like that. And d also, you understand what is d also. So we can write it like n into d raised to minus 1. Okay, with this n d raised to minus 1, operate. We will find out dou E divided by dou A1. Okay, at the end we will substitute for n and d, and then we will get our real value. Okay, so dou E divided by dou A1 is equal to, that is first function, that is n, into derivative of the second, that is equal to minus 1 by d square, right? Minus 1 divided by d square plus second function, that is d raised to minus 1, into derivative of the first, that is here I have to write one more. Okay, that is derivative of d raised to minus 1 is minus 1 by d square into again dou d divided by dou A1. Okay, that also I have to write. Dou d divided by dou A1. Okay, plus d raised to minus 1, that is second function, plus derivative of the first, that is dou n divided by dou a1. Okay, and that is equal to dou n divided by, we can write it like dou n divided by dou a1, that is a common factor. No, that is not common factor. 1 by d is the common factor. Okay, 1 by d. I will write 1 by d at the end. So dou n divided by dou a1 minus what is remaining here is dou d divided by dou a1, dou d divided by dou a1 into n divided by d. N divided by 1 by d is taken as the common factor from both terms. So let me write it here into 1 divided by d. Okay, so dou n by dou a1 minus dou d by dou a1 into n by d into 1 by d is equal to 0. Okay, now we can find out dou e divided by dou a2. Dou e divided by dou a2. Dou e divided by dou a2 is equal to, we can write it directly from this one. It will be similar to this. That is dou n divided by dou a1 a2 minus dou d divided by dou a2 into n divided by d into 1 divided by d. That is dou d by dou a2. Okay, and both of these, that is dou e by dou a1 and dou e by dou a2 should be equal to 0 according to our equation. Like നമ്മൾ ഈ പറഞ്ഞ equation അനുസരിച്ച്, ഈ equation അനുസരിച്ച് രണ്ടും 0 ആയിരിക്കണം. So both of these are equal to 0. This is equal to 0 and this is also equal to 0. Now we can from this equations, these two equations, either 1 by d is equal to 0 or the quantity which is inside the bracket is equal to 0. Okay, but 1 by d cannot be 0. If 1 by d is equal to 0, if 1 by d is equal to 0, what does it mean? It means that then it indicates that d is equal to infinity. Okay, d is infinity means the denominator of that term is infinity. What is that denominator of this term? That is the integrals SAA, SBB, SAB, etc. will be equal to 0. That is not possible because it indicates that it will be infinity. Okay, it indicates that we have infinite wave function. That is not acceptable. Okay, so since infinite wave functions are acceptable, this is not possible. Okay, so this is not a possible condition. So what is the possible condition? The quantity inside the bracket should be equal to 0. Okay, so we can write it like dou n divided by dou a1 minus dou d divided by dou a1 into n divided by d is equal to 0. Okay, and also dou n divided by dou a2 minus dou d divided by dou a2 into n divided by d is equal to 0. So we have two equations, right hand side of which are 0. Now let us find out dou n by dou a1, dou d by dou a1, dou n by dou a2 and dou d by dou a2. And finally, after finding out all these things, we will substitute in these equations. So let us go for dou n by dou a1. Dou n by dou a1 നമുക്ക് കണ്ടുപിടിക്കാം. Dou n by dou a1. Dou n by dou a1 is equal to, so we have to know what is n. What is n? Here is n. This is n. a1 square HAA plus a2 square HBB plus 2a1 a2 HAB. That is n. Okay, so let me write it here just for our reference. Otherwise, we will forget what is n. Since you cannot see n, I will write it here. N is equal to a1 square HAA, a1 square HAA plus a2 square HBB, a2 square HBB plus 2a1 a2, 2a1 a2 HAB, HAB. Okay, that is n. So dou n by dou a1 is equal to 2a1 HAA, 2a1 HAA, plus 2a2 HAB, 2a2 HAB. Okay, that is dou n by dou a1. And also we can find out dou n by dou a2. Dou n divided by dou a2 is equal to 2a2 HBB, HBB, right, plus 2a1 HAB, HAB. Okay, you may be getting why when we are differentiating with respect to a1, this term, the differential of this term is 0, because we are differential. It's a partial differentiation with respect to a1. At that time, the terms including a2 square, okay, that will be 0. Okay, so that is why when we are finding out dou n by dou a1, the derivative of this one becomes 0, and we are considering only those terms with a1 only. And here also the same. Okay, so that is dou n by dou a2. Now let us find out dou d by dou a1. So we have to know what is d. I will write what is d here. D is equal to what was d, the denominator, that is a1 square s aa plus a2 square sbb plus 2a1 a2 SAB. That was D. So from here we can find out dou D by dou A1. So dou D divided by dou A1 is equal to 2A1 SAA, and the second term, that will be vanished, and then 2A2 SAB. Okay, and dou D divided by dou A2 is equal to 2A2 SBB plus 2A1 SAB. Okay, that is dou D by dou A2. Now we can substitute dou n by dou A1, dou n by dou A2, dou D by dou A1, and dou D by dou A2 in our equations. Okay, we will substitute in our equations. So let us substitute here in this equation for this one. In this equation we will substitute, and also we will substitute in this equation. Okay, and let us substitute in the first equation. Dou n by dou a1 minus dou d by dou a1 into n by d into 1 divided by d is equal to 0. That is the equation that we are using first. The first equation is we will be substituting this equation. Dou n divided by dou a1 plus dou d by minus dou d divided by dou a1 into n by d, n divided by d into 1 n by d is equal to 0. Okay, because we took okay, in these two equations only. Okay, I was pointing another equation first, not this one. These two equations. ഈ രണ്ട് ഇക്വേഷനിലാണ് നമ്മൾ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യാൻ പോകുന്നത്. Okay, so let us substitute in this equation first. Then dou n by dou a1 എന്ന് പറയുന്നത് എന്തായിരിക്കും? Dou n by dou a1 2a we can substitute 2a1 HAA, 2a1 HAA plus 2a2 HAB plus 2a2 HAB, that is dou n by dou a1. Okay, then minus dou d by dou a1. Dou d by dou a1 minus dou d by dou a1. Then this one minus 2a1 s a minus 2a2 s a b. Okay, dou d by dou a1 into n by d. N by d is numerator by denominator. What is that? Actually e. Okay, that is e. That is equal to 0. Okay, so we have an equation here, and in this equation we can cancel 2 from all the terms. 2 from all the terms, no problem. Then what is remaining? We have the terms with the a1 and the terms with the a2. Let us put the terms with the a1 together. Then a1 is a common factor. A1 into h a minus saa minus saa a1 into haa minus saa. Where is that? Okay. Dou d into e. Okay, this is multiplied by e. There is one term here, e also. Sorry. I forgot to include the term here, e, because it is dou d by dou a1 into e. Dou d by dou a1 into n by d. N by d is e. So we have to multiply these two terms with e. Okay, so one e is also here. So we can write saa into e, or we can write it like e into saa. So haa minus e saa plus a2 into then HAB minus ESAB is equal to 0. Is equal to 0. Okay. Then we have another equation. That equation is obtained by substituting the terms in the second equation. What is that equation? Second equation is this one. Dou n by dou a2 minus dou d by dou a2 into n by d is equal to 0. Okay, dou n by dou a2 in this equation. Dou n by dou a2 minus dou d by dou a2 minus dou d divided by dou a2 into n by d, or n by d is equal to e is equal to 0. Okay, so we are going to substitute in this equation. First one, dou n by dou a2. Dou n by dou a2 is equal to 2a2 hbb 2a2 hbb minus 2a2 hbb minus not minus, plus 2a1 hab plus 2a1 hab plus 2a1 hab. Okay, then minus dou d by dou a2 into e. So dou d by dou a2 is this one, that is minus 2a2 sbb into e minus 2a1 sab into e is equal to 0. So let me cancel 2 from all the terms. Okay, from all the terms, and put the a1 terms and a2 terms separate. Okay, a1 terms together first. A1 into h a1 into h ab. Okay, hab minus e into sab okay, then plus a2 into a2 terms together, a2 into hbb minus a2 into sbb into e, therefore esbb. Okay, these are a2 terms, and that is equal to 0. So we have two equations. Okay, this equation Let me call this as equation 1 and this is equation 2. Okay, and we have two equations here. And these two equations, and equation number 1 and equation number 2, you know what is these equations are called? What these equations are called? These are called as secular equations. Secular equations. Secular equations. Equation 1 and equation 2. 1 and 2 are called as secular equations. Secular equations. We already learned this while learning variation theorem. Okay. And these secular equations, they will have a trivial solution if you consider a1 and a2 as 0. Then both equation number 1 and equation number 2 will be correct, because if a1 and a2 are 0, the left hand side of both equations will be 0. That is a trivial solution. Okay. If you want to have a non-trivial solution, okay, then what is the condition? If you want to have a non-trivial solution, you may be remembering, yeah, the determinant of the coefficients of a1 and a2 should be 0. Okay, so the non-trivial solution will be obtained by constructing the determinant of the coefficients of a1 and a2 and equating that determinant with 0. Okay, the determinant of the coefficients of a1 and a2 is determinant HAA minus ESAA. Then the second term is HAB minus ESAB. Then the next row, that is HAB minus ESAB, HBB minus ESBB. Okay, and this is the determinant of the coefficients of a1 and a2, and that should be equal to 0. Okay, and this determinant is called a secular determinant. Secular determinant. This is a secular determinant. Okay, here what we can rearrange this secular determinant, or we can simplify this secular determinant such a way that we can assume that HAA is equal to HBB, and this is because both hydrogen atoms are alike, right? HAA and HBB are similar, or they are equal, because both hydrogen atoms are alike. Both hydrogen atoms are alike. Okay, and also we can say that HAB is equal to HBA. Okay, you know what is the reason? Because H cap is Hermitian. Okay, and we can also write it like SAA is equal to SBB, that is equal to 1. Why it is 1? Because the functions are normalized. SAA means integral 1SA d tau. If 1SA is a normalized function, integral 1SA d tau is equal to 1, and 1SB is also a normalized function. So SAA is equal to SBB is equal to 1 because of the normalization, because the functions are normalized. Okay, and we can write SAB is equal to SBA is equal to S. Okay, yes. So that is an integral, yes. And we can simplify the secular determinant, which is equal to 0, by substituting, by taking into consideration these relations. So HAA, we can write HAA, the secular determinant will become HAA Okay, minus ESA becomes minus E only because SA is equal to 1. And the second term HAB minus ESAB, that is equal to minus ES. Okay, then HAB minus ES minus ES, and then HAA because HBB is equal to HAA. That is why I wrote HAA here. HAA minus E, and this is equal to 0. So we have simplified the secular determinant here. So if you are expanding this determinant, we can write it like HAA minus E the whole square minus HAB minus ES the whole square is equal to 0, right? What we have done here, HAA into HAA minus E into HAA minus E, that is HAA minus E the whole square minus then HAB minus ES and HBAB minus ES, the product of these two. So this minus this will be equal to 0. This is how the determinant is expanded. Okay, so that is equal to 0. Then we can write HAA. HAA is equal to HAA, not HAA, is equal to HAA minus E the whole square is equal to then this term will go to the other side, then it will be HAB minus ES the whole square. Okay, or HAA minus E is equal to HAA minus E is equal to root of this one. The root of this can be plus or minus HAB minus ES. Okay, so we have two conditions here. HA minus E is equal to plus HAB minus ES, or HA minus E is equal to minus of HAB minus ES. Well, let us consider both cases. Let us first consider HAA minus E is equal to minus of HAB minus ES. Okay, let us consider this first. So HAA minus E is equal to minus HAB plus ES. Okay, so we can write it like HAA plus HAB is equal to, we will take this minus E to the other side, then it will be plus E here, and E is a common factor, then E into 1 plus S. Okay, so we can write E is equal to HAA plus HAB divided by 1 plus S divided by 1 plus S. So we have one expression for E, HAA plus HAB divided by 1 plus S. And we have another condition from here, that is HAA minus E can be equal to plus HAB minus ES. Okay, positive quantity of this one, plus of this one, that is HAA minus HAB is equal to, the E will go to the other side, then E into 1 minus S, right? So E is equal to HAA minus HAB divided by 1 minus S. HAA minus HBAB divided by 1 minus S. So we have two expressions for E, the energy here. So one expression for energy is HAA plus HAB divided by 1 plus S, Let me call this as E1, okay, and the other expression for energy is HAA minus HAB divided by 1 minus S. Let me call this as E2. So we have two solutions for E, because the secular equation itself was a second order secular equation, and we have two solutions for E from this secular equation. E1 and E2 are the solutions for E. Now we have expressions for E, and E1 and we have the solution for E are E1 and E2, and this calculation of E1 and E2 now requires the evaluation of certain integrals. Which are those integrals? The calculation of E1 and E2 requires the evaluation of HAA. Okay, this is an integral, and it requires the evaluation of HAB, right? And it also requires the evaluation of the integral S. Okay, so these three integrals should be evaluated. So let us go for the evaluation of these integrals. Now HAA is equal to, what is HAA? That is integral 1SA h cap 1SA d tau. You may be remembering HAA is equal to integral 1SA h cap 1SA d tau. This was what we abbreviated as HAA. So let us expand this. That is equal to integral 1SA h cap. We already defined h cap. That is equal to minus half del square minus 1 by Ra minus 1 divided by Ra minus 1 divided by Rb plus 1 divided by R, that is h cap. Then 1 as B 1 as A d tau. Okay, and that is equal to integral 1SA minus half del square minus 1 divided by RA. Okay, I take only these two terms. RA 1 as A d tau minus integral 1SA. Now I take this part of the Hamiltonian. Okay, 1SA, not this part. Okay, 1 divided by RB 1 as A d tau, and now I am going to take the last part of the Hamiltonian, that is plus integral 1 as A sorry integral 1 is A 1 divided by R 1 is A d tau. Okay, so this is how I have expanded this HAA, and now you can look at here, minus half del square minus 1 divided by RA. What is that? That is the Hamiltonian for hydrogen atom A. If you are considering hydrogen atom A as an individual hydrogen atom, then the Hamiltonian for the hydrogen atom A is minus half del square minus 1 by RA. That is the Hamiltonian. This is the kinetic energy part, and this is the potential energy part. The RA is the distance between the electron and the nucleus A. Okay, so this is the Hamiltonian for the hydrogen atom A. So we can write it like Hamiltonian for hydrogen atom A operated over 1 as A, the wave function for the hydrogen atom itself. Okay, so we can write it like integral 1 s A h cap A 1 as A d tau, that is equal to the EH, that is the energy of the hydrogen atom, because h cap psi is equal to E psi, right? That is the eigenvalue equation, or it is a Schrodinger wave equation. This is the Hamiltonian for the first the hydrogen atom A. Therefore, this is the energy of the hydrogen atom. So we can write it like EH. So 1 as A EH, oneness a dito, oneness a dito, okay, oneness a dito, and then we have another integral, that is second integral, that is this is a second integral. Integral 1 say 1 by RB 1 say dito. Okay, here 1 by RB, that is the RB actually is the distance between electron and the nucleus B. Okay, so 1 by RB actually is the repulsive potential energy operator for the nucleus B. Okay, so this is we can call this as the potential energy of the potential energy of Coulombic attraction between electron and the nucleus B. Okay, because this operator is for the nucleus B. So it is a potential energy of Coulombic attraction between electron and the nucleus B. And let me call this integral as in J. Okay, let me call this as J, because J is equal to 1 SA 1 by RB 1 SA dito. Okay, J is equal to 1 SA integral 1 SA integral sorry, I'm going to take my brush. Okay, yeah, I got it. 1 SA 1 by RB 1 by RB 1 SA dito. This is integral J. So let me write it as J here. So this is equal to J. I can write it like minus J here. And the last integral, okay, integral 1 SA 1 by R 1 SA dito. R here is the internuclear distance. So let us consider that the internuclear distance is a constant. Okay, it is not constant actually. You may be remembering how we learned the Born-Oppenheimer approximation. Okay, just for a particular case we are considering R as a constant, means we are considering the system such that A and B doesn't move each other, relatively there is no position difference, then the R will be a constant, and then we will solve this equation, the entire equation. And the same we can do for different values of R. Okay, so for a particular calculation we are taking R as a constant, therefore we can put the R outside, then it will be like 1 divided by R into integral 1SA 1SA dito. So that is EH into integral 1 SA 1 SA dito, because integral EH is energy value that can be taken outside the integral sign. So it will be integral EH into integral 1 SA 1 SA dito. Actually integral 1 SA 1 SA dito is equal to 1, because 1 SA is a normalized function. Therefore we can write it like EH, because integral 1 SA 1 SA dito is equal to 1. EH minus J plus 1 divided by R into integral 1 SA 1 SA dito, that is equal to 1. Okay, so this is equal to EH minus J plus 1 by R. So HAA is equal to EH minus J plus 1 by R. Here you have to remember that we defined we have defined one integral here as J. J is equal to integral 1 SA 1 divided by RB 1 SA dito. Okay, now we can go for HAB. That is equal to integral 1 SA H cap 1 SB dito. This is HAB. Okay, so we can write it like integral 1 SA H cap. What is H cap? Minus half del square minus half del square minus 1 by R B minus 1 by R A. Okay, I put R B first and then R A after that. I have some intention for that. You might have already understood why it is like that. minus 1 by RA plus 1 divided by R 1 SB d2. Okay, so that is equal to integral 1 SA minus half del square minus 1 divided by RB 1 SB d2. Okay, so I have taken the first two parts of the Hamiltonian. Now I go for the second part, then it is again minus integral 1 SA 1 divided by RA 1 SB d2. Okay, 1 SB d2. Then the last part, that is 1 divided by R, okay, integral, sorry, plus integral 1 SA 1 divided by R 1 SB d2. Okay, that is equal to integral 1 SA, integral 1 SA, and what is this? Minus half del square minus 1 by RB. That is the Hamiltonian for the hydrogen atom B. Okay, that Hamiltonian is operated over the wave function for the hydrogen atom B. So that will be equal to EH 1sB, where EH is the hydrogen atom. Whether it is hydrogen atom A or hydrogen atom B, okay, that doesn't matter. When the hydrogen atom A and hydrogen atom B are individual hydrogen atoms, both hydrogen atoms are alike. Therefore, the energy of both of them can be considered as EH. You don't need to write it EHA and EHB, because EHA and EHB will be same, because both of them are individual hydrogen atoms. So we can write it like EH 1sB d2, 1sB d2 minus, we have another integral here, integral 1SA 1 by RA 1sB d2. We are going to define this integral as K. K is equal to integral 1SA 1SA 1s 1 by RA 1 by RA 1SB d2. This is second integral that we are going to define as K. Okay, and then we can write it like minus K. Then we have the third integral, that is 1SA 1 by R 1SB d2. R is taken as a constant, so we can take it out, 1 by R into 1SA or 1SB d2. Okay, so that is equal to EH into integral 1SA 1SB d2, EH into integral 1SA 1SB d2, 1SA 1SB d2 minus K plus 1 by R into integral 1SA 1SB d2. That is equal to EH into, what is integral 1SA 1SB d2? You may be remembering how did we term this integral 1SA 1SB d2? That is equal to S, right? So we can write it like S, EH into S minus K plus, this is also S, integral 1SA 1SB d2 is equal to S. So we can write it like S divided by R. So EH into S minus K plus S divided by R. This is HEAB. So we have HAA and HAB, and now we are going to substitute for HAA and HAB in our equation for E1 and E2. Okay, E1 is equal to HAA plus HAB divided by 1 pieces. So E1 is equal to HAA plus HAB divided by 1 plus S. 1 plus S. So that is equal to, what is HAA? HAA is equal to, it is here, EH minus J plus 1 by R. EH minus J plus 1 divided by R plus HAB, that is EHS minus K plus S divided by R, the whole divided by 1 plus S. 1 plus S. Okay, that is equal to, we have two terms with EH. Let us put those terms together so that we can take EH as the common factor. EH into 1 plus S, 1 plus S. Then we have minus J minus K, right? So we can write it as minus of J plus K, minus of J plus K. Then we have 1 divided by R and S divided by R. 1 by R is a common factor there. So 1 by R into 1 plus S, the whole divided by 1 plus S, right? And that is equal to EH minus J plus K divided by 1 plus S, okay, plus 1 by R, 1 divided by R, because 1 by 1 plus S and 1 plus S will be cancelled from the first term and the third term. Okay, so EH minus J plus K divided by 1 plus S plus 1 by R. That is the expression for E1. The expression for E1. And now we can go for the expression for E2. Expression for E2. E2 is equal to, what is the expression for E2? E2 is equal to HAA minus HAB divided by 1 minus S. That is E2, right? So this is equal to HAA is equal to, what is HAA? That is EH minus J, EH minus J plus 1 by R, 1 divided by R, minus of HAB, that is equal to minus EH into S, and then we had a minus K there, because we have a minus sign here, then it will become plus K, then we had a S by R, plus S by R there, it will become minus S by R, okay, minus S by R divided by 1 minus S. So that is equal to EH common factor into 1 minus S, 1 minus S, and then we have minus of J plus J minus K, sorry, we can write it like minus of J minus K, then what is remaining? 1 by R. 1 by R is a common factor, so plus 1 by R into 1 minus S, 1 minus S, the whole divided by 1 minus S, okay. So that is equal to EH, 1 minus S will be cancelled, minus of J minus K, J minus K divided by 1 minus S, okay, plus 1 divided by R, and 1 minus S will be cancelled. So this is the expression for E2. So we have the expression for E1 and E2 here, okay. Now from these two expressions, from E1 and E2, expression for E1 and E2, E1 is EH minus J plus K plus 1 divided by 1 plus S plus 1 by R. E2 is equal to EH minus J minus K divided by 1 minus plus 1 by R. So what are the what are the things that we have to evaluate in order to find out E1 and E2? Okay, this E1 and E2 requires the evaluation of J, because in both cases J is there, K is there, and S is there, okay. So for a particular value of R, and if you know the J, K and S values, then we can find out and the the E1 and E2 values. So we have to have J value, K value, and S value for a particular R. Okay, and it is possible to derive the expressions for J, K, and S, but here I am going to give you the final equations for J, K, and S. J is equal to 1 divided by R into 1 minus 1 plus 1 plus R into e raised to minus 2R. E raised to minus 2R. Okay, that is the expression for J. And the expression for K is equal to 1 plus R into e raised to minus R. E raised to minus R. And the expression for S is equal to 1 plus R square divided by 3 into e raised to minus R. Okay, so these are the expression for J, K, and JK and S. Okay, so if we have this J, K, and S for different values of R, we can plot E1 and E2 against the different values of R. So what we are going to do is we are going to evaluate J, K, and S for each value of R, and for each value of R we will also evaluate E1 and E2. Okay, I am going to use a software for this one. Okay, I have evaluated this integral, J, K, and S, E1 and E2 using Excel. Okay, you can do it very easily in Excel, and I have given the results in another software. This software is called Origin software. You can only see the values here because the active area of screen recording is much below. I will try to show you. Okay, now you can see it. Okay, so this is the Origin software. I have used this software in order to plot this one. Here I have given the values, which are these values given here. So let me put it a little bit down. Okay, yeah, you can see that I have given the R value here. I have given a particular value, R value, that is 0.5. Then I have found out J, K, S, E1 and E2, because you know that everything depends upon R. Right? നിങ്ങൾ നോക്കിക്കോളൂ, ജെയുടെ കെയുടെ എസിന്റെ വാല്യൂ എല്ലാം ഡിപ്പെൻഡ് ചെയ്തിരിക്കുന്നത് എന്തിനാണ്? ആറിന് മാത്രമാണ് ഡിപ്പെൻഡ് ചെയ്തിരിക്കുന്നത് അല്ലേ. നിങ്ങൾക്ക് ആറിന്റെ വാല്യൂ കൊടുക്കാന്നുണ്ടെങ്കിൽ ജെയും കെയും എസും കണ്ടുപിടിക്കാം. അങ്ങനെ കണ്ടുപിടിച്ച് വെച്ചിരിക്കുന്നതാണ് ഞാൻ ഈ ആർ വാല്യൂ. ആക്ച്വലി ഞാൻ ഈ വാല്യൂസ് കാൽക്കുലേറ്റ് ചെയ്ത് എക്സലാണ്, അതിനുശേഷം ഞാൻ ഒറിജിനിലോട്ട് പ്ലോട്ട് ചെയ്തിരിക്കുകയാണ്. ഓക്കെ, ഒറിജിനിലോട്ട് പ്ലോട്ട് ചെയ്തിട്ട് പ്ലോട്ട് ചെയ്യാനുള്ള ഒറിജിനിലേക്ക് പേസ്റ്റ് ചെയ്തിരിക്കുകയാണ്. ഇത് ഇങ്ങനെ പേസ്റ്റ് ചെയ്യേണ്ട കാരണം ഇവിടെ പ്ലോട്ട് ചെയ്യാൻ കുറേ കൂടെ എളുപ്പമാണ് ഈ സോഫ്റ്റ്വെയറിൽ, അതുകൊണ്ടാണ് ഇങ്ങോട്ട് പേസ്റ്റ് ചെയ്തത്. അപ്പോൾ ഞാൻ ഇവിടെ ആറിന്റെ വാല്യൂ കൊടുത്തിട്ടുണ്ട്. ഫസ്റ്റ് കോളത്തിൽ കാണുന്ന ആറിന്റെ വാല്യൂ ആണ്. ഫോർ എ പർട്ടിക്കുലർ വാല്യൂ ഓഫ് ആർ 0.5 എന്ന് പറയുന്ന വാല്യൂവിന് വേണ്ടി ഞാൻ ജെ കണ്ടുപിടിച്ചിട്ടുണ്ട്, കെ കണ്ടുപിടിച്ചിട്ടുണ്ട്. ഐ ഹാവ് ഇവാലുവേറ്റഡ് എസ്, ഐ ഹാവ് ഇവാലുവേറ്റഡ് E1 and I have evaluated E2. Then I changed the value of R. Okay, then I changed the value of R into 1. Then I evaluated all these terms for different values of R from 0.5 to 5. Okay, for different values of R I have found out the values of E1 and E2. Here you can see E1, here you can see E2. ജെയും കെയും എസും കണ്ടുപിടിച്ചതിന് ശേഷം E1ന്റെയും E2ന്റെയും എക്സ്പ്രഷനകത്ത് ജെയും കെയും എസും സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്താണ് ഈ വാല്യൂസ് കണ്ടുപിടിച്ച് വെച്ചിരിക്കുന്നത്. ഓക്കെ, ആൻഡ് നൗ യു ക്യാൻ സീ ദാറ്റ് you look at only the R value and how the E1 value is changing. Okay, see, R value is 0.5 and at that time the E1 value is 1.07. ഇനി ആറിന്റെ വാല്യൂ ഞാൻ കൂട്ടുകയാണ്. കൂട്ടുമ്പോൾ E1ന്റെ വാല്യൂ എന്ത് കുറയും നോക്ക്. E1ന്റെ വാല്യൂ കുറഞ്ഞ് വരും കണ്ടോ. അപ്പോൾ R കൂടുന്നതിനനുസരിച്ച് E1ന്റെ വാല്യൂ കുറഞ്ഞ് വരും. ഇവിടെ നിങ്ങൾ ഓർത്തിരിക്കാനുള്ള ഒരു പ്രത്യേക കാര്യം എന്ന് പറയുന്നത്, ഇതൊന്ന് ശ്രദ്ധിക്കുക. നമ്മുടെ ഈ E1ന്റെ എക്സ്പ്രഷനകത്ത് നോക്കുക. E1ന്റെ എക്സ്പ്രഷൻ എന്ന് പറയുന്നത് എന്താണ്? EH മൈനസ് J പ്ലസ് K ഡിവൈഡഡ് ബൈ 1 പ്ലസ് ഇൻറ്റു 1/R എന്നാണ്. ഈ EHന് ഞാൻ 0 എന്നാണ് കൊടുത്തിരിക്കുന്നത് കേട്ടോ. ഹൈഡ്രജൻ ആറ്റത്തിന്റെ ഈ എനർജി, ഹൈഡ്രജൻ ആറ്റത്തിന്റെ വണ്ണസ് ഓർബിറ്റലിന്റെ എനർജിയാണിത്. ഈ എനർജി എന്ന് പറയുന്നത് ഞാൻ 0 ആയിട്ടാണ് കൊടുത്തിരിക്കുന്നത്. അതിനർത്ഥം ഹൈഡ്രജൻ ആറ്റത്തിന്റെ വണ്ണസ് ഓർബിറ്റലിന് 0 എനർജി ആണെന്നല്ല. അത് ഞാൻ ഇങ്ങനെ കൊടുത്തിരിക്കുന്നതിന്റെ കാര്യം എന്ന് പറയുന്നത്, അത് 0 ആയി കഴിഞ്ഞാൽ E1ന്റെ വാല്യൂ എത്രയായി? ഐ ജസ്റ്റ് വാണ്ട് ടു കമ്പയർ E1 ആൻഡ് IH. E1 0 ആയിട്ട് ഫിക്സ് ചെയ്ത് കഴിഞ്ഞാൽ E1ന്റെ വാല്യൂ എത്രയായിരിക്കും എന്നാണ് ഞാൻ കമ്പയർ ചെയ്യുന്നത്. ഐ വാണ്ട് ടു നോ what is the relative value of E1 with respect to EH. That is why I fixed EH as 0. EHനെ പിടിച്ച് 0 എന്ന് സ്കെയിലിൽ 0 കൊണ്ടുവച്ചു. അത്രേ ഉള്ളൂ. അതുപോലെ E2നെ അതുപോലെ തന്നെയാണ് കാൽക്കുലേറ്റ് ചെയ്യുന്നത്. E2ന്റെ എക്സ്പ്രഷനിലുമുണ്ട് EH അല്ലേ? In that expression also I took EH as 0. Then I found out the relative value of E2. അപ്പോൾ സത്യത്തിൽ നിങ്ങൾ ഇവിടെ കാണുന്ന നമ്മുടെ കോളത്തിൽ കാണുന്ന E1ന്റെയും E2ന്റെയും വാല്യൂ absolute values അല്ല. The values that you are finding here is a relative values. Okay, relative to EH. അപ്പോൾ ഇവിടെ E1ന്റെ വാല്യൂ 1.0707 എന്ന് കണ്ടു കഴിഞ്ഞാൽ അതിന്റെ അർത്ഥം the value of E1 for the R value when internuclear distance 0.5, for the internuclear distance 0.5, the value of E1 is 1.07 greater than the value of EH. Okay, EHനേക്കാൾ 1.07 കൂടുതലാണ് അർത്ഥം. ഇനി അത് ഇങ്ങോട്ട് വരികയാണ്. അപ്പോൾ EHനോട് ഇങ്ങോട്ട് വരുന്നതോടെ E1ന്റെ വാല്യൂ കുറഞ്ഞു വരും എന്ന് പറഞ്ഞാൽ അത് EHനോട് അടുത്തുകൊണ്ടിരിക്കുകയാണ് അല്ലേ? എന്നിട്ട് ഇവിടെ നോക്കുക, ഈ ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് 2ലേക്ക് വരും. when the internuclear distance is 2, the E1 value goes to negative. Negative means it is going below the value of EH. EHന്റെ വാല്യൂവിനേക്കാൾ കുറയുകയാണ് ഇവിടെ ചെയ്യുന്നത്. മനസ്സിലായോ? അപ്പോൾ 2ലേക്ക് വരുമ്പോഴത്തേന് E1ന്റെ വാല്യൂ എന്ന് പറയുന്നത് ഹൈഡ്രജൻ ആറ്റത്തിന്റെ വണ്ണസ് ഓർബിറ്റലിന്റെ വാല്യൂവിനേക്കാൾ കുറയുന്നു E1ന്റെ വാല്യൂ. മനസ്സിലായോ? അപ്പോൾ അത് ഇങ്ങനെ കുറഞ്ഞു വരികയാണ്. എന്നിട്ട് ഇവിടെ 2.5 ആകുമ്പോൾ അത് 0.06 വരെ കുറയുന്നു. പിന്നീട് അങ്ങോട്ട് നോക്കിക്കഴിഞ്ഞാൽ ആ വാല്യൂ എന്ത് ചെയ്യാണ്? വീണ്ടും അത് 0യോട് അടുത്തുകൊണ്ടിരിക്കുകയാണ്. പിന്നെ 0.5 ആകുന്നു, 0.4 ആകുന്നു, 0.3, 0.2, 0.01 അങ്ങനെ 0യോട് അടുത്തുകൊണ്ടിരിക്കുകയാണ്. അപ്പോൾ when it is 2.5, the value is minimum അല്ലേ? 2.5 the E1 value is minimum. Okay, it is lower than the value of EH, and EHനേക്കാൾ ഏറ്റവും മിനിമം ആകുന്നത് ഇത് 2.5 ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് ആകുന്നില്ല. അതാണ് ഇത് കാണിക്കുന്നത്. മനസ്സിലായോ? അപ്പം നമ്മളുടെ പ്ലോട്ട് നോക്കിക്കഴിഞ്ഞാൽ ഈ വാല്യൂസ് ഞാൻ പ്ലോട്ട് ചെയ്തിട്ടുണ്ട്. നിങ്ങൾ നോക്കുക എങ്ങനെയാണ് പ്ലോട്ട് അപ്പിയർ ചെയ്യുന്നത് എന്നുള്ളത്. ഇങ്ങനെയാണ് ഇരിക്കുന്നത് കണ്ടോ? ഇതാണ് R ആക്സിസ് എന്ന് പറയുന്നത്. R ആക്സിസ് ഇതാണ്. ഓക്കെ, ഐ വിൽ എക്സ്പാൻഡ് ഇറ്റ് എ ലിറ്റിൽ ബിറ്റ്. ഓക്കെ, ദിസ് ഈസ് ദ R ആക്സിസ്. ഇതാണ് R ആക്സിസ്. ഇവിടെ വാല്യൂ ഇങ്ങനെ കൂടി വരികയാണ്. ഇവിടെയാണ് ഈ ആക്സിസ്, എനർജി ആക്സിസ്. ഇതിനകത്ത് ഈ റെഡായിട്ട് ബ്ലാക്ക് ആയിട്ട് പ്ലോട്ട് ചെയ്തിരിക്കുന്നതാണ് E1 എന്ന് പറയുന്നത്. അപ്പോൾ ഇവിടെ നോക്കിയോ, E1 എന്ന് പറയുന്നത് when the internuclear distance is very less, then the E1 is greater than the value of EH. അപ്പോൾ E1 എന്ന് പറയുന്ന സത്യത്തിൽ ഇവിടെ എന്താ? നമ്മളുടെ നമ്മൾ കൺസ്ട്രക്ട് ചെയ്തിരിക്കുന്ന മോളിക്കുലാർ ഓർബിറ്റലിന്റെ എനർജിയാണ് E1. 2 എനർജി നമ്മൾ കൺസ്ട്രക്ട് ചെയ്തിട്ടുണ്ട്. സോ there are 2 energies corresponding to our molecular orbitals, E1 and E2. അതിനകത്ത് E1 എന്ന് പറയുന്നത് അതിന്റെ വാല്യൂ EHനേക്കാൾ വളരെ കൂടുതലാണ് when the internuclear distance is very minimum. When the internuclear distance is increased, then the E1 value will decrease അല്ലേ? ഇനി അത് ഡിക്രീസ് ചെയ്ത് ഇങ്ങോട്ട് വരുമ്പോൾ 2.5 ആകുമ്പോൾ when the internuclear the energy is minimum, and when the internuclear distance is again increased, then the energy will again increase. അപ്പോൾ ഇത് നിങ്ങൾക്ക് ഒന്നുകൂടെ വ്യക്തമായിട്ട് കാണണമെന്നുണ്ടെങ്കിൽ ഞാൻ ഈ സ്കെയില് ഒന്നുകൂടെ വലുതാക്കി കാണിച്ചു തരാം. അതിന് തൊട്ട് മുമ്പായിട്ട് എന്താണ് E2ന് സംഭവിക്കുന്നതെന്നുകൂടെ ഒന്ന് നോക്കാം. ഓക്കെ, സോ വാട്ട് വിൽ ഹാപ്പൻ ടു E2? നമുക്ക് E2ന്റെ വാല്യൂസ് ഒന്ന് പരിശോധിക്കാം. when the internuclear distance is 0.5, E2 value was 2.33, ഒരു വലിയ വാല്യൂ ആയിരുന്നു. ഇനി ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് കുറച്ച് കൂട്ടി കൊണ്ടുവരികയാണ്. 0.5 ന്ന് 1 ആയി. 1 ആയപ്പോൾ ഇവിടുത്തെ E2ന്റെ വാല്യൂ കുറഞ്ഞു. ഇനി ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് വീണ്ടും കൂട്ടി, E2ന്റെ വാല്യൂ വീണ്ടും കുറഞ്ഞു. ഇങ്ങോട്ട് നോക്കുകയാണെന്നുണ്ടെങ്കിൽ the E2 value is continuously decreasing. it is continuously decreasing and it is approaching 0. അല്ലേ? ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് കൂട്ടി കൊണ്ടുപോകുകയാണെന്നുണ്ടെങ്കിൽ ഈ E2 വാല്യൂ 0യോട് അപ്രോച്ച് ചെയ്തുകൊണ്ടിരിക്കും. മനസ്സിലായോ? That is what we can see in the plot here. So the E2 value is given in the red plot. Okay, see when the R is increasing, the x axis R increasing. When R is increasing, then the E2 value is continuously decreasing like this. E2 value is continuously decreasing. അപ്പം അതിൻ്റെ അർത്ഥം എന്താണ്? ഇപ്പം നിങ്ങൾ നോക്കിക്കോളൂ, നമുക്ക് ഈ പ്ലോട്ടുകൾ ഒന്നുകൂടെ എക്സ്പാൻഡ് ചെയ്ത് നോക്കാം. ഓക്കെ, സോ ലെറ്റ് us expand this. അപ്പോൾ ഈ സ്കെയിൽ ഞാനൊന്ന് മാറ്റാൻ പോവുകയാണ്. 2.35 വരെ പോകുന്നില്ല, ഞാൻ ഏകദേശം ഒരു 0.5 വരെ പോകുന്നുള്ളൂ. 0.5 വരെ പോകും. ഓക്കെ, 5 or 6, 0.6 വരെ പോകും. ഇപ്പോൾ കണ്ടോ, കുറേ കൂടെ വിസിബിൾ ആണ്. സി when the scale is expanded, the graph is much more visible. ഇനി ഒന്നുകൂടെ നന്നായിട്ട് എനിക്ക് വിസിബിൾ ആക്കണമെന്നുണ്ടെങ്കിൽ ഇത്രയും കൂടെ വേണമെങ്കിൽ ഇവിടെ കുറയ്ക്കാം. ഈ സ്കെയിൽ ഒന്ന് കുറയ്ക്കാവുന്ന കാര്യമുള്ളൂ. 0.4 ആയിട്ട് മാറ്റാമെന്നുണ്ടെങ്കിൽ, if I it has 0.4, it is much better. Okay, see now the E1 value initially was greater than the value of the hydrogen atom itself. അല്ലേ? ഹൈഡ്രജൻ ഇൻഡിവിജ്വൽ ആയിട്ട് ഹൈഡ്രജൻ ആറ്റം ഇരിക്കുന്നതിനേക്കാൾ കൂടുതലായിരുന്നു ഇവിടുത്തെ എനർജി വാല്യൂ എന്ന് പറയുന്നത്, H2 മോളിക്യൂളിന്റെ എനർജി വാല്യൂ എന്ന് പറയുന്നത്. Then that energy value is continuously decreasing when the internuclear distance is increasing. Then when the internuclear distance is here, that is when it is 2.5, okay, the energy is minimum. ഇതാണ് എനർജി മിനിമം ആകുന്ന കേസ്. ഈ കേസിലെ ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് 2.5 ആണ്. അപ്പം 2.5 അറ്റോമിക് യൂണിറ്റ് ആണ്, ഏത് ഓർത്തിരിക്കണം, ഇതെല്ലാം അറ്റോമിക് യൂണിറ്റ്സിലാണ് എഴുതിയിരിക്കുന്നത്. So when the internuclear distance is 2.5 atomic unit, the energy is minimum. When the internuclear distance is again increasing, the energy will increase. So there is a point here for which the energy is minimum, and the internuclear distance corresponding to that minimum energy, okay, and that internuclear distance will be corresponding to the stable arrangement of the two nuclei in the H2 plus ion. ഇപ്പോൾ H2 plus ion ഏറ്റവും സ്റ്റേബിൾ ആയിട്ടിരിക്കുന്നത് രണ്ട് ന്യൂക്ലിയസുകളും തമ്മിൽ ഈ ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസിൽ ഇരിക്കുമ്പോഴാണ്. അതായത് മിനിമം എനർജിക്ക് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള ഈ ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ്, ഇറ്റ് ഈസ് അറൌണ്ട് 2.5 ഹിയർ, 2.5 atomic units. So when it is at 2.5 atomic unit, the energy is minimum. Okay, and that distance is called the bond distance. Okay, അപ്പോൾ ഈ കേസിലെ ബോണ്ട് ഡിസ്റ്റൻസ് ആണ് എന്ത്, 2.5 atomic units എന്ന് പറയുന്നത്, 2.5 atomic units. So here the energy is minimum, and the minimum energy corresponds to an internuclear distance R is equal to 2.5 atomic unit. Okay, 2.5 atomic unit means it is around 1.32 angstrom. ഇപ്പോൾ ഹൈഡ്രജൻ മോളിക്യൂൾ അയോൺ നമ്മൾ കൺസിഡർ ചെയ്യുമ്പോൾ രണ്ട് ന്യൂക്ലിയസുകൾ തമ്മിൽ ഈ ഒരു ഡിസ്റ്റൻസ് ആയിരിക്കുമ്പോൾ, മീൻസ് വെൻ ഇറ്റ് ഈസ് 1.32 angstrom, at that time the energy will be minimum. So that is called the bond distance in the H2 plus ion. Okay, and also we found that the energy corresponding to this is the minimum energy. Okay, if we are increasing this energy from here to here, okay, and then the energy will reach 0. And 0 എന്ന് പറഞ്ഞാൽ അതിൻ്റെ അർത്ഥം എന്താ, എനർജി 0 ഫോർ ഹൈഡ്രജൻ ആറ്റം. അതായത് ഇൻഡിവിജ്വൽ ഹൈഡ്രജൻ ആറ്റങ്ങളായിട്ട് അതിനെ ബ്രേക്ക് ചെയ്യണമെന്നുണ്ടെങ്കിൽ ഈ എനർജി ലെവലിൽ നിന്ന് അതിന് ഇവിടെ വരെ വരണം. The energy has to be increased from here to here if the hydrogen molecule ion has to be braked into the individual atom, or in order to break it into the individual atom as hydrogen atom and hydrogen ion, H and H plus, H പ്ലസുമായിട്ട് അതിനെ ബ്രേക്ക് ചെയ്യണമെന്നുണ്ടെന്നുണ്ടെങ്കിൽ ഇവിടെ നിന്ന് ഇവിടം വരെ വരണം. അതായത് ഇത്രയും എനർജി, ഈ എനർജി ഡിഫറൻസ് അതിന് പ്രൊവൈഡ് ചെയ്യണം. ആ എനർജിയാണ് നമ്മൾ ഡിസോസിയേഷൻ എനർജി എന്ന് പറയുന്നത്. അപ്പോൾ ആ ഡിസോസിയേഷൻ എനർജി എന്തിന് കറസ്പോണ്ടിങ് ആണ്, ഈ എനർജി എത്രയാണെന്ന് നോക്കിയാൽ മതി. ദിസ് ഈസ് how much far below this energy when compared to the energy of the individual atom. അപ്പോൾ ഈ എനർജി എത്രയാണ്, നമ്മുടെ ടേബിളിനകത്ത് കണ്ടതാണ്. this energy, the 2.5 corresponding energy in the 0.-0.06483. Energy 0.06483, 0.06 atomic unit. So that is the minimum energy. That is energy corresponding to dissociation energy. So dissociation energy is equal to 0.065 atomic unit, and if we are converting this to electron volt, that is 1.77 electron volt. Okay, for 1.77 electron volt കൊടുത്തു കഴിഞ്ഞാൽ എന്ത് ചെയ്യും? നമ്മളുടെ ഈ H2+ അയോൺ എന്ന് പറയുന്നത് സ്റ്റേബിൾ ആയിട്ടിരിക്കുന്ന H2+ അയോൺ എന്ന് പറയുന്നത് H ആയിട്ടും H+ ആയിട്ടും അത് ഡിസോസിയേറ്റ് ചെയ്ത് മാറും. Okay, that is what this curve is indicating. Okay, and also we have another curve here for E2, and in the case of E2, always the E2 values are above the EH values. അപ്പോൾ എപ്പോഴും അത് പിന്നെ 0 ആയിട്ട് അടുക്കുന്നതെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ എൻ്റെ അർത്ഥം the molecule is dissociating. അല്ലേ? അപ്പം ഇതാണ് നമുക്കുള്ള രണ്ട് എനർജി വാല്യൂസ്. So one energy profile is corresponding to bonding, because when the molecule is in that energy profile, then it can acquire a minimum energy, and that minimum energy is less than the energy of the individual hydrogen atom. അപ്പോൾ നമ്മുടെ ഇൻഡിവിജ്വൽ ഹൈഡ്രജൻ ആറ്റത്തിനേക്കാൾ കുറവാണ് നമ്മുടെ ഇവിടുത്തെ എനർജി എന്ന് പറയുന്നത്. അതിൻ്റെ അർത്ഥം എന്താ? ഇറ്റ് ഈസ് ഗോയിങ് ടു ബി മോർ സ്റ്റേബിൾ. അല്ലേ? ഇപ്പോൾ H2+ അയോൺ ഫോം ചെയ്യുന്നത് കൊണ്ട് എന്തെങ്കിലും പ്രയോജനം ഉണ്ടെന്ന് അർത്ഥം. അപ്പോൾ ഹൈഡ്രജന്റെ അറ്റോമിക് ഓർബിറ്റലിനേക്കാൾ കുറഞ്ഞ ഒരു എനർജി ലെവലിലേക്ക് അത് പോകും, സിസ്റ്റം പോകും, if it is kept at 2.5 atomic unit, or if it is kept at 1.32 angstrom. അല്ലേ? അപ്പോൾ ഇവിടെ കൊണ്ടുവെക്കുകയാണെന്നുണ്ടെങ്കിൽ സിസ്റ്റത്തിന്റെ എനർജി കുറയും, so that the system will be stable. So this situation corresponds to bonding. The other situation actually corresponds to the anti-bonding, because that energy is always above the energy of the atomic orbitals. Okay, so today I am going to wind up this session here. We only considered the energy in this session. ഇനി നമുക്ക് അതിൻ്റെ അറ്റോമിക് ഓർബിറ്റൽസ്, അതിൻ്റെ മോളിക്കുലർ ഓർബിറ്റൽസിനെ പറ്റി കൂടുതൽ അടുത്ത ക്ലാസ്സിൽ ഡിസ്കസ് ചെയ്യാം. What we have done today is we applied the quantum mechanics for treating the H2+ ion. Okay, and we have seen that H2+ ion can be formed because it can reach an energy level which is less than the energy of the hydrogen atom itself. So there is a situation corresponding to the bonding with a less energy profile, and therefore this is possible. അപ്പോൾ നമുക്ക് അങ്ങനെ ഒരു എനർജി സിറ്റുവേഷനെ പറ്റിയാണ് നമ്മളിന്ന് ഡിസ്കസ് ചെയ്തത്. ഓക്കെ, നമുക്കിനി അടുത്ത ക്ലാസ്സിൽ ബാക്കി കാര്യങ്ങൾ ഡിസ്കസ് ചെയ്യാം. താങ്ക് യു ഫോർ വാച്ചിങ്.